Hi, in this video of InkPod, we're going to be starting with the system of equations where the number of equations is lesser than the number of unknowns. This is actually precisely the case where m is less than n, and so far we had been dealing with cases where m was equal to n. With m is less than n, you come to the concerns of something called consistency, and I'm going to be discussing that further very soon. The following video after this is going to actually talk about the rank criterion for consistency. Again, this is a very important portion of the system of linear equations unit, so please make sure that you understand the different types of solutions which can exist under different scenarios and the kind of methods that you can use for each one of them. Obviously, because you wouldn't know before solving what kind of solution it is, therefore, as I had said, it is the Gaussian substitution method, which is the universal method for solving the system of equations. Okay, so when m is less than n, there are two types of solutions which are possible. One is the infinite solution scenario, and the other is the no solution scenario. The infinite solution scenario is the consistent system of equations, and the no solution case is the inconsistent system of equations. Consistency essentially has got to do with the existence of a solution. If a solution exists, then it is a consistent system. If a solution does not exist, it's an inconsistent system, period. Consistent solutions can be of two types. There is infinite solutions and there is unique solutions. In the case of m is less than n, which is the number of equations is lesser than the number of unknowns, you don't have a unique solution. You cannot possibly have a unique solution. So the idea of a unique solution is already out of the picture, which means that all you're left with is either an infinite solution. Okay. Like I had said, Gaussian substitution is our preferred method. So let's see a few examples. Now this is a system of equations which you are expected to solve. I'm going to start using the Gaussian substitution method. I will write out the augmented matrix. That's the first step. So 1 minus 2, 3, 3, 1 minus 4, 5 minus 3, 2. And you have 6 minus 7 and 5. R2 goes to R2 minus 3 R1. So you have 1 minus 2, 3, 6, 3 minus 3, which is 0, 1 minus minus 6, which is 1 plus 6, which is 7, minus 4, minus 9, which is minus 13, minus 7, minus 6 into 3, 18, which is minus 25, and 5 minus 3, 2, 5. Okay. The next step is R3 goes to R3 minus 5 R1. Again, understand that I'm just trying to or rather get forward the matrix, which is the augmented matrix, into its upper triangular form. So that is the reason I'm doing all of these steps. So you would have 1 minus 2, 3, 6, 0, 7, minus 13, minus 25. And now you have 5 minus 5, which is 0, minus 3, minus minus 10, which is minus 3 plus 10, which is 7, 2 minus 15, which is minus 13, and 5 minus 30, which is minus 25. Now, because these two rows have actually ended up being the same, if you just do a simple R3 goes to R3 minus R2, then you can write it out as 1 minus 2, 3, 6, 0, 7, minus 13, minus 25, and 0, 0, 0, 0. Okay. Now the next step in the Gaussian method is just to open the system of equations out. I'm going to do that in another color. Okay. So So you would have something like x minus 2y plus 3z is equal to 6. 7y minus 13z is equal to minus 25, and 0 equals 0. So you can see here that essentially the number of equations has become lesser than the number of unknowns, because one of the equations has been reduced to a 0. I mean, when you say that m is less than n, the reason you are saying this is because, as you can see, the number of unknowns here is 3, x, y, and z, right? Whereas the number of equations after you have gone to the point of solving it out, you can see that after reduction, so after reduction, m is actually equal to 2, which is less than 3, right? Which means that m is less than n. Okay. So now that you have this, what you will now get is the following. So you have 7y minus 13z is equal to minus 25. Let z be any arbitrary number equal to k, which is this is any arbitrary number. Okay, and this is precisely what you're supposed to write. Let z be equal to k, which is any arbitrary number. Then 7y minus 13k is minus 25, which means 7y is equal to 13k plus minus 25. Y is equal to 13k minus 25 upon 7. Similarly, you can substitute the value of y back into this equation to get the value of x. Let me just show you how that is done. You have y is equal to 13k minus 25 upon 7. Okay, and then you have x minus 2 into this plus 3k is equal to 6. So in that manner, you would get x equal to 5k minus 8 upon 7. You have the solution right here. The point is that you have to assume this particular line right here. You say let z be any arbitrary number equal to k, then the solution of the equation is going to be as follows. And the way you realize that m is less than n is when this particular situation happens, where one equation is reduced to an entire row of zeros. So straight off the bat, you might you might look at this system of equations and think it is, it may be m equal to n, it may be m greater than n, it may be m less than n, which is why Gaussian substitution method is such a powerful method, because irrespective of what the solution is going to look like, irrespective of whether the number of equations may turn out to be less than the number of unknowns, the Gaussian substitution method is going to apply. That's why it's important to understand how the Gaussian substitution method is applied in a variety of cases. And I have tried to cover as many cases as possible in the previous videos and in the forthcoming videos also. But like I had said earlier also, the key is to practice this out. Okay, so this is one way of solving. Now, because you have m is less than n, and you have a consistent solution here, so you will actually say that you have infinite solutions here. The reason you have infinite solutions is because of the fact that k can take any value, and the values of x and y would change accordingly. Alright, but a solution exists, so it's a infinite solution. Okay. Now we come to the following system of equations, where you have x minus 4y plus 7z is equal to 8. Okay, so let me just write out the augmented matrix. Okay. So you have 3 minus 3 equal to 0, 8 minus 12 is equal to 8 plus 12, which is 20, minus 2 minus 21, which is minus 23, and 6 minus 24, which is minus 18. And you have 7 minus 8, 26, 31. Okay. Then you would do something like R3 goes to R3 minus 7 R1 and so on and so forth. Let me just take you to the solution. So you have R3 minus R3 goes to R3 minus 7 R1. You get to this point. Now here is where it is very interesting to contrast the two problems that we have discussed so far. In the earlier problem, you had these two rows as identical rows, and you simply said that if you subtract one from the other, one of them is reduced to a row of zeros, and then you solve the equations. Now here what is going to happen is actually not that. When you say R3 goes to R3 minus R2, you have a row of zeros here, but you don't have a zero here, alright? Which means that when you open this system of equations out, you would have something like x minus 4y plus 7z is equal to 8, 20y minus 23z is equal to minus 18, but you would have 0 equal to minus 7. This is not possible. This is a mathematical inconsistency. So when you have a mathematical inconsistency as follows, naturally this is not possible. Therefore, there is no solution. Okay. So as soon as you get a mathematical inconsistency, you say no solution. And this is an inconsistent system, as I had, said earlier. So it is important to take note of all of these, types of solutions, and understand that when you come to the conclusion of a mathematical inconsistency, it's always a good idea to recheck that you haven't made a calculation error. I mean, in general also you should be rechecking your solutions, but to make this statement, it's a very strong statement, so please be sure that it is actually true before you make it. Okay, so as I had said, consistency is the existence of a solution, unique or infinite. Inconsistency is no solution. It is a mathematical inconsistency. When m was equal to n and determinant a was not equal to 0, you had a unique solution and it was consistent. Okay, and you could use the following three methods, as we have discussed. And when m is less than n, you have either a no infinite solution or a no solution, and you have a consistent and inconsistent systems naturally. And the method that you use is the Gaussian method. Thank you.